Okay, so so first off, homework 3 is due today. The solution's online, and I don't have any. I'm not going to accept late submissions since you all have the homework. So what I'll say is, if it's not up here, let's get it up here. Now, homework number 2. I have homework number 2 in my hand. A few of you, I guess, who aren't here, I have that now. So hopefully they come in because I need their homework today. So I've turned that back. By and large, on homework 2, you all did pretty well. There were a few, there was a few minor things, like little things here and there, but honestly, really didn't glean any, like everybody needs to look at this, or you all are having problems with this. That really wasn't the case. By and large, it seems like everybody did very, very well. So what I want to do is get into exam review. So what I like to do on these exam reviews is this, okay? So let's take a look at this. First off, right off the bat, this is what's on the exam. Fundamentals of stress and strain, axially loaded members, and torsionally loaded shafts. Okay? So let's talk about the exam format. I want everybody to know exactly what they're getting into on Tuesday. So it's closed book and closed notes, but you are obviously allowed a calculator. As for what calculator, as long as it doesn't have a Wi-Fi connection, I really don't care what calculator you use. You can use whatever you want. It could be a graphing calculator, scientific. I don't care. I'm easy to get along with. You have a formula sheet that you're allowed, an 8.5 by 11. You can write on the front. You can write on the back. You can put whatever you want on it, except for worked out examples. You can put formulas, equations, unit conversions. You can put procedures, step-by-steps. Whatever, I don't care. Just no worked out examples. And that's not for my benefit, it's for yours. If you're doing a problem on the exam and you're in the zone and you accidentally grab a value from the example that you had on your formula sheet and it shows up in your problem, things will just go nuts. So I don't want you to, it might seem like it helps, but usually it adds a layer of confusion. On top of that, I'm a big believer in that muscle memory. What you write is what you know, and I don't want you to go into the test remembering only that one problem that you put on your formula sheet. I want you to remember the procedures and the equations and the process. Okay? Now, I'm going to mention this at the end, and I'm going to point at some people, but I want you to try and be on time. Okay? And here's what I mean by that. We are going to start at 8 o'clock sharp on the dot. Okay? If everybody who is here and prepared to take the exam, if everybody who is supposed to be here is here early, like if everybody shows up, let's say at 7:55, we'll start at 7:55. I'll start early, but everybody's got to be here. Okay? If you're not, then we're going to start at 8 a.m. Okay? Now I'm going to have a scratch paper, like some of the problems have some space where you can work on the exam. Some of them you'll probably need some paper on the side. I'll have scratch paper and I'll have a stapler. So I've got all of that. I have no problems if you want to rip the test apart, take the staple out and do that. I got no problems with that. I'll probably staple everything at the end. Okay. As for the format, okay, so the first problem, so there's 4 problems on the exam. The first problem is going to be a series of short answer questions. Okay. And when I say short answer questions, I mean that. I mean short answers. I've had students write Shakespearean sonnets for some of these problems that are only worth 2 points, okay? So usually the problems are worth anywhere from 2 to 5 points apiece, they're really small problems. Now I totally understand if, you're looking at the problem and you know the answer and it takes you 8 or 10 words to get out the answer, whereas it might take somebody else 5 or 6 or 2 to 3. These are a very short answer. If you're writing 2 or 3 sentences or a paragraph for these, you're probably going a little too far. I'm looking for the big ticket points to the question. So here's an example. Okay, I might ask you something like, what is the ratio of applied force to cross-sectional area known as? Okay, it's stress. Okay, that's it. Stress. S-T-R-E-S-S. Move on to the next one. Don't go arose by any other name or whatever. Don't go into. You don't need to provide an elaborate. Just say stress and move on. Okay. So I'm not gonna get you on that. Okay. Let's also look at this yellow box. This yellow box refers to what homeworks are going to be, covered on the exam. And when I say lecture notes 01 to 03, if you go to the, if you go to Blackboard, okay, if you go to Blackboard, I've got the lecture notes listed in PDF. So there's like lecture notes 1, which is fundamentals, lecture notes 2, which is axial loads, and so on and so forth. That's what's on the exam. So you could take it one step further and say the exam covers like example 1 to example, what, like 15? Is that like the last one we did? I don't remember the number. It was like 14 or 15, something like that. So that's the coverage of topics on the exam. If you want to get more specifically, more specific into it, here is the coverage on the exam, which, by the way, every one of these slides is on Blackboard right now. So I will be more than happy to pause for a sec if you need to write anything down, but also, bless you, if you miss something, don't worry, it's up there. So let's talk about fundamentals of stress and strain. So you need to be able to compute normal stresses and strains in basic structures. So basically what I mean is you have to know what's going on with the equations of equilibrium, how you cut sections, support reactions, stuff like that. You all know how to do that. I want you to be able to identify relevant properties on a stress-strain curve, like what's Young's modulus, what's the yield stress, and so on and so forth. Using stress-strain relationships and relevant data. So if you've got a stress-strain curve or if you've got the appropriate data, tell me what's the modulus of elasticity. Tell me what the yield stress is. Tell me what the ultimate tensile stress is. Tell me what the shear modulus is if I give you E and Poisson's ratio. Just the very basic stuff. And also make sure that you have a general understanding of what a factor of safety is. The idea of the actual stress compared to the allowable stress. Let's see. Axially loaded members, okay? So make sure that you know how to compute the response of an axially loaded member. What's the load? What's the stress? What's the strain? What's the deformation? I mean, stress is P over A. Strain is change in length over the original length. Deflection's PL over EA. All that stuff. Make sure that you understand that. Make sure that you can do this for members with a constant load area or a varying load or area. Make sure that you can handle members that are statically indeterminate. That's internally or externally, and make sure that you can handle members subjected to thermal loads. As for torsionally loaded shafts, make sure that you can compute the response. So what I mean, like how much torque there is, what's the stress, what's the strain, what's the angle of twist, all of that stuff. Constant or varying torque or diameter, and make sure that you can handle, again, indeterminacy as well. And the other thing with torques, like if axially loaded members had that little caveat with thermal loads, torsional members have power-torque relationships, so make sure that you can handle that. And one of the things I did give you on this packet is this, okay? So hopefully what is in the next few slides will greatly help you out in the preparation of your formula sheets. Because what I have here is what I think are the most fundamental formulas for this test, okay? And so if I go into fundamentals of stress and strain, I have an image of just a generic stress-strain curve. I have absolutely no problem if you put something like this on your formula sheet. No problem with that at all. We have what is the fundamental definition of stress? What's the fundamental definition of strain? We have Poisson's ratio. We have what's the relationship between normal stress and normal strain? What's the relationship between shear stress and shear strain? I have a definition for the factor of safety. I also have just a generic stress-strain curve for steel. As for axially loaded members, what I put on the slide was this. As I said, the total deflection in an axially loaded member is whatever its deflection due to mechanical loads are and whatever its deflection due to thermal loads are. So if you have a bar that is not heated or cooled at all, then its delta thermal is 0, and just handle this accordingly. Now as for, let's say, delta mechanical, if you have a varying load or area, like if the load changes or the area changes along the member, then integrate. If not, then just PL over EA. For thermal deflection, if you have a varying temperature, like if it's getting hotter on one end of the bar or cooler on one end of the bar, then integrate. If not, it's just AL delta T. And based on these definitions, if you know the definitions for deflection, well, you can determine, well, what's the strain, what's the stress, and so on and so forth. So everybody okay with that? Torsionally loaded shafts. So over here on the right, I have the angle of twist formula, which is really where a lot of this comes from. So the angle of twist for a varying torque or J is integrated. For a constant torque in J, just TL over GJ. I have the formula for shear stress. Now, of shear stress and shear strain. The ones that are referencing rho are stresses from the center. So at the center, the stress is 0, and then it increases outwards. So remember, maximum shear stress and shear strain occur at the extreme fiber, or the wall of your shaft. So tau max is TR over J. Gamma max, the shear strain, is TR over GJ. As for how to compute J, we only have 2 formulas that you need to remember, J for the shaft and J for the pipe. We do have the power-torque relationship over there on the left, and then the shear modulus if you're not given the G value specifically, but you're given E and Poisson's ratio, there's your formula. So in this one PowerPoint, I think I've given you everything. Like, that's pretty much every formula that we've utilized this semester so far. Now, we got more coming later, but that's it. That is your first exam in a nutshell. I'm going to shut up for a little bit and let you all ask some questions. So, the floor is yours. Does anybody have any questions? Yes, sir.
Can you go over how to handle redundancy with thermal loading?
Thermal loading. Okay. So the question was how to handle redundancy with thermal loading. So what you're talking about is a scenario where you have a bar that's, let's say, clamped on both ends, and you're going to heat it up or cool it down, right? Okay. All right. So let me go back to this, because I think we had an example that was just like this. Here we go. This was a perfect example of this, because this was an example of exactly what you're talking about. So first, short answer is go through example 9 in a nutshell. But I want to go through example 9 with you so that everybody's okay. Okay. And this is the nice thing about using the screen, is I don't have to rewrite this stuff on the board. I can pull up the stuff that we wrote together. So I love this. I love technology. All right. So here's the bar, and you've got all the fundamental information. I'm not going to go through all that because you all know what it is. But one of the things to observe is what's going on with the temperature. Okay. So this bar is initially at 70 degrees Fahrenheit, and then the temperature drops to 0 degrees Fahrenheit. So what's happening is the bar is cooling down. It's getting colder, okay? Now, if I'm just holding this bar like this, if the bar is not fixed to the wall, if it's just sitting right here on the table, and I cool it down, what is the bar going to want to do? Is it going to want to get shorter or get longer? It's going to want to get shorter, okay? But that's not what's going on here. The bar is being held at a constant length by the wall, okay? So if the temperature drops, the wall is responding by yanking it back to 0. In other words, it wants to get shorter by, let's say, 2 inches, and then the wall is holding it back 2 inches, so it's yanking it. So anytime that you have a situation like this and the temperature drops, it puts the bar in tension, okay? So on the flip side, if you have a bar that is being heated up in this scenario, it's being put in compression, okay? And I don't think that that's that hard of an analogy to understand. I mean, imagine that I've got my hands like this, and I have a balloon in my hand. And suddenly the balloon got hotter and hotter and hotter. Well, the balloon's going to want to do this, right? And so in order to keep my hands where they are, I have to push on the balloon, right? So I have to push on it in compression. It's the same thing, okay? So what we do from an analysis perspective is this. Now I got to find it. That's example 12, 10, 10. There we go. Did I finish the problem? Yeah, I did. Okay. All right. So what we did is for this problem, we removed one of the walls. Like, we just picked one and said, let's just assume that wall is gone. Now, really what we were saying is this, was that we were taking the bar and sort of, you know how it's fixed between the walls? We were taking the bar and just sort of putting it over here. And we were saying, well, if the temperature drops, how much shorter is it going to get? And so how much shorter it's going to get is just alpha delta TL, and that's just plug and chug. So plug and chug, and it gets shorter about 0.045 inches or something like that. So that temperature drop will cause it to shorten that amount. And I'm saying it's negative because it's getting shorter and because the temperature change is going down. So then what I have to do is say, how much does the wall have to yank on it in order to pull it back? Okay? So I know my delta is 0.0455 inches, and I know E and A and L and all that. So what's P? So now I'm in this scenario, solve, and I get P is 27,000 some odd pounds, and if I've got that, I can determine stress. Okay? Does that make sense? Now, did I answer your question? Okay, what's that?
So we would, like, on an exam, a possible question could be like, a bar is subjected to thermal loading, calculate the deflection, and then using that, calculate the stress on the bar.
Possibly, possibly. Now, let me further that discussion a bit, okay? Without restraint, okay? Here's the bar, sitting right there, okay? Without restraint, I heat that up and cool it down. It's going to get longer and it's going to get shorter, whatever, okay? It's going to have a change in length, which means it's going to have a strain. But without restraint, without something holding it back, it's not going to have any stress, okay? Going back to the balloon, if I have a balloon right here and I heat that balloon up, it's going to expand, okay? But all that means is that it's getting bigger. It's undergoing strain. I do not generate stress until I take my hands and push it back, okay? So without some sort of restraint, without some sort of mechanical load being applied to it, you will not get stress. You'll get thermal strains all day long, but no stresses, okay? Does that make sense to you and everybody else? So you good? Everybody else? This is good stuff. This is like the stuff I like to talk about. So, I mean, keep it going. If you've got questions, this is the time. I mean, I want you to feel comfortable going into the exam, and I guarantee you, whatever question you come up with, somebody else is probably thinking of something similar. So don't be, shy. Yes, sir.
Yeah, sorry for
No, this is the time.
Okay, so we're not assuming the wall that we're, like, getting rid of, so to speak. We're not assuming that to cause any mechanical stress. It would have to be like an external load.
Well, okay, what I'm saying is with that wall there, it does cause mechanical stress.
Yeah, but when we're, like, assuming it to not be there to calculate the deflection.
Yes, yes. So to answer your question, what I'll say is this: if you look at the top scenario, like let's say this is the problem. Let's just say this is the problem, and it's fixed on one end and free on another. Okay, and I change the temperature. What's the deflection? That. What's the strain? Change in length divided by the original length. What's the stress? 0. If this was the scenario. With that wall there, that's not the case. And the reason why is if I don't want to draw it on the screen, but I'll say this. If here's my bar, right? Okay? And let's say I heat the bar up so it gets hotter and hotter and hotter. The way you get your mechanical stress is that the walls push back. That's how you get your mechanical load on it, is that the walls push back. If this support didn't exist, then you wouldn't get any mechanical load, and it would just expand freely. This is good stuff. So, is that good? This is good stuff. This is what I like to hear. All right? Keep it coming. Keep it coming.
When, like, either just generally, like, temperature or load or area or J are varying, are they going to be varying, like, in some, like, nth order polynomial, or will they always be linear?
That's a good question. So the question is, on the exam, are the areas and whatnot going to be varying to some weird amount? Is it going to be linear or not? This is what I'll say. Okay, I think a reasonable assumption on this exam is that when in doubt, it will probably be either linear or not much more complicated than that. This is not Calc 2. Okay, so I'm not interested in your ability to, like, I could say, well, the load on this bar is defined by the sine of x squared, and then this is just a calculus problem, and we could do that, but that's not. I think at that point I'm not testing you on your understanding of mechanics of materials. I'm testing you on your ability to integrate the sine of x squared, and at that point, that's what Calc 2's for, or whatever. So yeah, one of my philosophies when I formulate tests is I'm testing you on the stuff we're talking about. Now, you know, am I indirectly testing you on your ability to perform arithmetic? Well, yeah, because you have to plug and chug into equations, so you have to add, subtract, multiply, and divide. So I guess I am testing you on your arithmetic ability. I can't get around that. I'm sorry, you decided to be engineers. You're going to do arithmetic. I don't know what to tell you. But I am not, that's what I'm not trying to do. I'm not trying to turn this into, you know, the sine of x squared e to the x. Your integrals that you need to do on this test will either be given to you if the functions are that complicated, or you can pretty much assume they're either going to be linear or not much more complicated than that. And I'm not going to say any more than that because it is an exam and I got to keep some cards close to the chest. So. Did that answer your question? Everybody else okay with that? Keep it coming. This is your time. I want this review to be dynamic. Come on. Really? Like that was dirty. What that was.
On the equation sheet, it is okay, like, not to have examples, but we can have like a sketch of, you know, like, so we can have like graph that, or like a sketch of like, you know, a pipe or something.
Yeah, I have a problem with that. Like if you're wanting to sketch out a pipe to say this is the outer diameter and this is the inner diameter and this is how you compute J, if you want to write that the inner diameter is the outer diameter minus 2t or something like that, you can do that. You can put that stuff. I don't have a problem with that at all. It's your formula sheet. Put what you think is appropriate. I just don't want you to just regurgitate this example, because when you take the exam, I might give you something different. And you're going to look to this example and go, well, this isn't the same. What do I do? You know? Well, it's a test. I mean, there's going to be, you know, a couple, you know, curveballs thrown at you. But if you understand the process, I guarantee you can handle it. I guarantee it.
Short answer stuff, is that all going to be basically like qualitative stuff in the lectures, or is there going to be like stuff buried in the chapter somewhere
No.
that we never talked about?
No, well, let me say this. When you boil it down, when it comes to the theories and the topics that we discuss in this course, I mean, there's a lot of terminology and there's a lot of phenomena that you've seen in this class that you probably didn't think of, like we actually have a name for Poisson's ratio and things like that. But in the end, like, stress is P over A. You know, it shocks me that you're able to take that and turn it into a 900-page textbook. Like, I don't get it, you know. I really don't. I mean, if you open up the FE reference manual for mechanics and materials, it's like 6 pages. It has everything you need. Everything you need. So that is kind of shocking. Now, let me say this. There are some things in some of those chapters that we did not discuss in class, and that is for a specific reason, or a specific couple of reasons. First off, I don't like to double dip, okay? And what I mean by that, let's take a topic we're going to talk about way later in the class, which is columns. Columns like to buckle, okay? So near the end of the semester, we're going to deal with elastic buckling and how you handle buckling for members in compression. Now, when you read that chapter, it goes through all the theory that we're going to talk about in class. But then, if you go past that, there are some things that the book discusses that we're not going to discuss in class. Here's the specific. The book discusses the AISC column curves. We're not going to discuss that in here. There's a very clear reason. You want to learn about it? Take steel design. We'll talk all about it and that much more, okay? So I don't want to talk about stuff in the book that you're going to talk about in other courses, okay? I don't really talk about stress concentrations in here, but you mechanicals are going to talk about that probably in machine element design because that's relevant to you. I'm not saying it's not relevant to us. We just handle it through code provisions and whatnot. So there's stuff in the book that I didn't talk about because I know you will talk about it in other courses, and I'm not going to test you on that. I'm not going to be the guy who said, well, it was on page 33, so subparagraph 4, you should have read it. I'm interested in your ability to be an engineer. I understand that you all should be smart enough that once you understand the fundamental concepts, which is what I test you on, and I'm interested in your ability to navigate, if you understand that, with enough time and enough resources, you can figure this stuff out. I can't teach you everything. I'm trying to generate a group of engineers that can figure stuff out on their own, because that's what true engineering is. You're going to leave this university and get a job doing something we never taught you how to do, but that's engineering. I mean, if it was just doing the same thing you learned in school, well, we could write computer programs to do that. We wouldn't need engineers, okay? Your job is to think critically and think, you know, and to use your cognitive abilities to solve problems that people haven't seen before. And so I'm just making sure that you understand the fundamentals. I'm not that professor. But let me say this: if we discussed it in class and it's in the notes and what have you, it is fair game. That is fair game. So. Yes, sir.
So for step shafts, what's your recommended approach for handling?
A step shaft. You mean like the homework problem?
Yeah.
Okay. That's a great question. What I would do for that, and I would think that my answer is going to apply to whether or not we're talking about axial loads or whether or not we're talking about torsion. Because remember, axial loads and torsion share some very unique similarities. You know, the loads are along the axis, the equations are very similar. So what I'm saying is going to apply to both. When you have a step shaft like the one you're talking about one that's like fixed on one end and free on the other, okay? And so what I would do is, let's say that shaft is made of 4 segments. Let's just say it's 4. I don't know, 4, 7, it doesn't matter. Let's say 4 segments. If it's made of 4 segments, I would cut 4 sections, 1 through each shaft. As for which direction you look, I would always look towards the free end, okay? The reason I'd look towards the free end is because if you talk about that first shaft, the one that's way on the tip, you cut a shaft, you look, the only thing you're going to see is the load being applied. So if it's 20 pounds, that's 20 pounds, right? If you look at the next shaft, look to the right, you'll see 20 and 30. So that makes this 50. You know what I mean? So once you cut those sections and look, you'll determine it's either the internal load or the internal torque inside each of those shafts. At that point, once you know how much force or how much torque is inside each shaft, it's just section properties and stresses and deformations, just plug and chug at that point. I would recommend probably like maybe writing yourself up a table and saying, okay, for each shaft, what is the length? What is the E value or the G value? What's the area or what's the J value? And just sort of organizing it. I also think right off the bat, if you haven't already done so, and it's not already the case, get everything in consistent units right off the bat. You know, if it's metric, make sure all your forces are in newtons or kilonewtons or whatever. If it's distances, make sure they're all in millimeters or meters. You know, so let's talk about metric. It's very easy to say, well, my length is 5 meters, and it's asking for a deflection in 5 millimeters, and it's easy not to convert that length to 5,000 millimeters or what have you. So do that right off the bat, okay? Because you don't want to find yourself like in the middle of the problem and you're doing this math and you're getting a deflection of 8,000 miles or something like that's not right. You know what I mean? So don't put yourself in that scenario because you didn't take the time to convert everything to a consistent unit system at the beginning. Okay? Do that. So it's a couple pieces of advice. Ensure your unit systems are consistent. Ensure that you're organizing your data appropriately. If you do that, that is 70-80% of the battle right there. Okay? I've been doing this job for a while. And I can tell you something, units still get you off, okay? I just tell you right now, units, I have seen it screw people up. And even when they know what they're doing, it's the units that get you. If your units aren't consistent at the very, very beginning, go ahead and convert them. Like if it says 5 feet, no, 60 inches, you know? Just do it right at the beginning, you know? You will save yourself some headache, guaranteed. Here's another thing when it comes to test-taking strategy. Going back to the Shakespearean sonnets, I have seen students write Shakespearean sonnets for a problem that's worth 2 points. And then they have a problem that's worth 30 points and they have 5 minutes left. guys, you know, time management, okay? If a problem is worth 25%, you should reserve 25% of your time for it. And I know that seems like, well, duh, but I know also, like, during the exam, you get in the zone and you might not be thinking of that. So I'm saying that, like, I want to see you do great. It makes my job a whole hell of a lot easier if everybody gets hundreds. And man, I can have this thing graded in 5 minutes. Like, what are you talking about? I don't like, you know, grading. I don't like grading it when everybody's getting everything wrong. I'm like, oh God, now I got to sit here and, you know, figure out everything. Which, let me also talk about how I grade exams, because it takes me a while. And what I do is this. I make myself an Excel spreadsheet, and I solve the problem out. And I do every little nitpicky calculation. Then I take each person's problem. If the problem is right, mark it, move on. If it's wrong, I start changing values until I get what you got. And it's either like a unit conversion, or you use the wrong equation, or whatnot. And once I know what you did wrong, I take off for what you did wrong, I make a note of it, and then I go to the next student. Okay? And I'm pretty methodical about that, because I remember being in your shoes, and I remember something, it would just drive me up the damn wall, is I'd have a buddy of mine, and we both miss the same, like we do the same thing, and they'd get 6 points taken off, I get 10 points taken off. I go, wait, well, hold on, you know. I do my absolute best to avoid that. I kind of like that. It doesn't do you all any favors. Now, I will admit, there are some times that I get a student's problem. I have no idea what they're doing, but I do like to use the Sam's discount. So if a problem is worth, you know, 25 points, and they kind of know what they're doing, but they had so much stuff wrong, I'm like, minus 15, you know. I have done that before, okay? And also when it comes to the Sam's discount, if you start having these little, oh, here's -1 for units, oh, here's -1 for this, and I add it up and it's like 10 points off of a 15-point problem, I'll just use the Sam's discount or something and say like -8, you know, give you a wholesale deduction. I do that, okay? Because at that point, it's like, if you had that much stuff wrong with the problem, I've made the point that you had some issues. I don't need to, like, do that to you, you know. I try not to.
So in like a scenario where you have like a two-part problem where you have to calculate the first part and the second part, if you did the first part wrong, but the second part is right except for using that wrong number.
I give you full credit on the second part. That is true. I will do that. Let me say this. I do my best to avoid that on exams, but sometimes it's unavoidable, especially when you have a problem where there's a lot going on and you need to compute multiple things. It is what it is, you know. Like a thermal problem, you know, like if you go into a thermal problem, it's like, okay, what's the, you know, change in temperature to bring it to, you know, whatever, and you have to use the results from the first part to go on. Well, you kind of can't avoid that, you know. So I try and avoid it, but a lot of times it's impossible. So. It's your time. Anything else?
Can you give us
So that's a good question. All right. Here's what I'll do. If it's a torsion problem, there's 3 things you can expect. I'll either give you G, I'll either give you E and Poisson's ratio, or it's possible that I could say something like, okay, here's the stress and here's the strain, or what have you. What does the G value need to be in order to meet this criteria? I'm not going to give you the unsolvable problem. Like, I'm not going to do that. And another thing, I don't give, in this course, I don't give very many open-ended problems. In other words, there's no real problems in this class where, you know, it's like design and we could have 7 different answers and they're all right. I don't do that because I don't think that's what this course is about. This course is about understanding the mechanics. So there's, the stuff we do in here, there's one answer. My thought is, you know, my philosophy with this course is that if you understand the material in this course, you can then apply it to machine element design or design of thermal systems or concrete or foundations or steel design or what have you. And in those scenarios, you can have some open-ended experiences, but not here, you know. I give a homework assignment, for instance, in reinforced concrete design, and I always dread grading it because I'll get like 7 different answers that are all right, you know. They're all right because it's like an open-ended beam problem, and so one person could have a beam that's 14 inches wide and 20 inches deep with 4 number 7s, and somebody else could have a beam that's 12 inches wide and 24 inches deep with 3 number 8s, and they're both adequate designs. They're both adequate designs, and so I have to go through and check them all, and it sucks. But it's my labor for you all to go through the experience of design. That's fine. But in here, that's not what I'm after. And so, yeah, that isn't the case. I promise. Yeah. Yeah. So you won't have to worry about that. Like I said, I did the exam in about 20 minutes. So that's how long it took me to do it. And so I usually apply a rule of 3. So you should be good on time. I don't like to do that either. So, like I said, I'm not going to sit here and say that it won't be a challenge, but I would like to believe it's a fair challenge. I'm not in the business of, you know, creating an impossible Ninja Warrior course for you to navigate. I don't like doing that either. We got plenty of time. I mean, this is your time. I want you to feel comfortable going into Tuesday. So, what's that? No. Well, I'll say why for a couple reasons. One, I'd have no problem actually giving you or telling you a little bit about last year's exam if I taught it last year. I didn't teach it last year. So it's been a while since I've taught the class. So this exam kind of came from scratch as a result of that. Sort of its own unique thing. But there are some concepts and stuff I have borrowed from when I taught it back in the day. So no? Yeah. But let me follow that up by saying this. If you understand the concepts and you understand what we've done in class, the example problems that we've done, and the theory and the equations, I really don't think you're going to see anything that's like, you know, in class the professor showed us 2 + 2 = 4, you know, and the homework said determine the mass of the sun, you know, like. There's a meme about that. It's pretty funny. But I don't do that. Okay, there are a couple, you know, curveballs, but nothing that you can't handle. And another thing I'll say, once you get past my first exam, like, think of this question again for the second exam, and you'll see that, like, I do my exams in a very similar way. I have sort of a way of doing exams, and after you get through my first exam, they're all sort of the same format. So, like, for those of you who are in structural analysis, once you take this exam, the exam in structural analysis is going to be set up very similarly. You know, 1 set of short answer problems and 3 workout problems. So it'll be the same way. So.
A large preamble at the beginning of the test that I'm required to read. Big block of text.
All right, you got to tell me about the experience because like, what are you talking about? You can't just leave it like that. Like.
Well, you know, there's some classes where there's exams and there's just this huge giant block of text that you got to read through, and you know,
Like the Apple terms of service or something.
Yeah.
What?
And then homework, if we don't fold it the right way, he doesn't grade it.
Like,
He'll throw it in the board.
in my statics last semester, a kid came in late and ripped his homework out of the notebook and just walked up to the front. He was already late. He was standing there. Handed him the paper. And didn't sit there and looked at it. Crumpled
God.
Is there any
Soul crushing.
is there like formats that you want answers in, stuff like that? I mean, is that all
Apparently I wasn't kidding about this whole onset of acute post-traumatic. All right, let's get the couch out. Look, I'll go ahead and tell you, look, the front of the exam has a cover sheet, and all it has is your name. It has, just like, don't have your cell phone out, and like a couple sentences that says you can use a calculator and stuff like that. And then I just put a little table on the front that says problem 1 is worth this many points, and then when I hand it back to you, like, let's make up a number. If problem 1 is worth 20 points, I gave you 18 points. And so problem 2 is worth this many points, I gave you this many points. And other than that, I think all it says is just to show your work, The test had, like, the actual, okay, let's talk about this. The test itself, each problem has a space for you to put the answer, So, like, what's the stress in this bar? And there's like a line, just put it there. And then there's a scratch, you have scratch paper and you can put whatever you want on it. As long as I can read what you write, like, that's all I care about. I also am a partial credit guy. I don't know that I actually, like, came right out and said that, but I am a partial credit guy. But that can be a double-edged sword, okay? If you just say x equals 2, and that's wrong, and you give me absolutely no work to go along with that, I don't have much choice, okay? But if you give me x equals 2, and you provide the work, and I see you had a plus where a minus should have gone, that's a point off, and I'll move on, But show me what you did, okay? Because I'm all about your understanding of the concept. And if it's a little mistake, you're going to get a little point off. If it's a big conceptual error, you're going to get more points off. I take off more points if there's like a conceptual error, like you didn't understand like the idea, you will get more points off. But if it's, little, you'll get a little mistake. I'm not outcome determinative and stuff like that, And I also am pretty, like, rounding matters, but I'm not going to, detrimentally penalize you for it. 14.7 versus 14.6 minus 20 points. I don't do that, okay? Because there's a very good reason why I don't do that. And I know that the physicists and the scientific notation folks are going to go, that is an error in the world of science. Shame on you. Well, here's the thing. We're engineers, okay? When you solve for the required diameter of the torsional shaft and it comes out to 1.21 inches, what the engineer says is go with 1 1/4. They just use what's available. They just round that up to the most commonly available size. So even if you round differently from an actual application perspective, you're going to be fine. We also employ specifications and factors of safety calibrated based off statistical measurements of uncertainty. The long and short of it is, if somebody dies because of something like that, it's like that usually isn't the problem. It's usually because there is a fundamental conceptual error, like the rover that crashed into Mars because they used a different unit system. Well, it wasn't rounding. That's because everything was off by a factor of like 3, or I mean, it was way off. When the bridge, when the I-35 bridge collapsed in Minnesota, okay, that wasn't a rounding error. That was a design error. The plate was half as thick as it should have been. Like they didn't, like the statics on the plate didn't work. Like there's 2 plates, So that, that wasn't a rounding error. That was like, they didn't get it, Or they did get it and they made a mistake, but it was a mistake. It wasn't rounding, okay? So I'll be honest, I'm really just not as concerned about that. And plus, even if I was, in the real world, once you all understand the concepts, you're going to write your own Excel spreadsheet anyways, and all the rounding issues are going to be washed out because you're just going to plug in the numbers and it'll carry out everything to 19 decimal places anyways. So that really doesn't matter to me, honestly. In practice, it's not a big deal. Everybody's like, who are you? What are you talking about? We never heard this crap before. I feel like some of you are like, I know he's saying this, but still. He's going to take off, isn't he? You're like, damn, Dr. Mike, you're getting kind of psychic on us now. We still got, I mean, are there any other conceptual questions? Anything that you all can think about? Anything at all? I want you to come away from the exam feeling challenged, but feeling it was fair. You know, that's what I want. So, all right. I'm getting the feeling the questions have been exhausted. This might seem silly, but I do this. Are you good? Are you good? Are you good? You good? You good? All right. So, let's recap our housekeeping. The exam will be Tuesday starting at 8 a.m. If everybody is here on time, we will start early. But everybody's got to be here that's here for the exam, okay? So if I take the roster and we're all here 5-10 minutes early, we'll start 5-10 minutes early. But if somebody's missing, like we're waiting until 8. So right off the bat, there's a couple people that didn't make it today. So like if you got their number and you want to give them a heads up, that's fine. Or if not, that's fine too. I won't be cutthroat about it. But really, all you're doing is sort of hurting yourself, because if they're not here, we're not starting. So, and when I say starting early, like we'll still go to 9:15, like we'll still go the whole time. So that'll be extra time on the exam. So again, if there's people that aren't here, and you know that they aren't here, have them let you know. Any other final questions? All right, we will see you all bright and early for the exam.